All right, let's begin. Welcome back. We're going to talk CS3510, and this is L02A, excuse me, L01B. And we're going to be talking about two things. We're talking about the master theorem and Mergesort. So you guys have all seen Mergesort in some context. Have you guys seen Mergesort before? Maybe you don't remember, something like this. Mergesort is, so what is the sorting regime, right? So sorting is a problem we want to study, and we have input of unsorted array, and the output is going to be a sorted array. Most commonly, it's not duplicated. It's sorted like in memory. Swaps are occurring. And we also usually do things in the comparison model, which means that comparing if two elements, A less than or equal to B, takes O1 time. Now, this is not true in general, but it's just like when you talk about sorting algorithms, this is what we wish to measure. Then we wish to measure in the comparison model, as the complexity grows, as a number of elements to sort, not as the size of an element or something strange. So this is the just what we mean by sorting. And again, we'll talk about quicksort as well later. But Mergesort is pretty easy as far as it goes. So we're going to have a one-indexed array of A1 to n. By the way, in most books, everyone indexes by 1, even though the computer indexes by 0. So it's just a old-fashioned thing that you may have to get used to in certain contexts. And as long as you're writing your pseudocode clear, if you're 0 indexing or 1 indexing, it shouldn't really matter. But here, the first element of this array is a 1, and this last element is at index n, right? We want to write a recursive algorithm. The point of Mergesort is not actually that we sort an array. I don't really care. The point of Mergesort is that it's recursive, and then we can study recursive algorithms with this example. But if we want a base case of a recursive algorithm, what is a base case sorted array? In some sense, what is the smallest sorted array we could ask for? Yeah. Yeah. You could even argue that a 0-size array is the smallest element, but I think 1 is small enough. If n equals 1, return A. So if n equals 1, if the array contains a single element, then the array is sorted. Like a proof by induction, it's very important that you have your base cases, because if you don't have base cases, it's just always wrong. Now what are we going to do? We're going to split the array in half. So we're going to say L takes on not just A of 1 to the floor of n over 2, the first half of the array, but it's actually going to take on the sorted version of that, right? So what this means is we call Mergesort recursively on the first half of the array, and then we call that L. And then we call R on the second half. Now, here's another thing about divide and conquer. In the real world, you may not be able to split your array up nicely in half. Don't care. In the algorithms world, we get just to assume everything is nice. Just assume n is a power of 2, and I don't need to do any floor function or ceiling function. Pseudocode in divide and conquer is much more pleasant to read than the actual implementation. Because when you actually look at an implementation of Mergesort, there's a little bit of casework. It's like, well, if n is odd, let's say you're splitting an array of size 5 in half. You have to now make a decision. Where does this middle element go? Does it go on the left? Does it go on the right? Doesn't really matter as long as you consistently make a decision. And then when you recursively call it let's say you split the array of size 5 into 3 plus 2. Well, now when you split 3 in half, you have to make another decision on the middle element, and so on. So it's kind of a little messy looking, but it doesn't really matter. It's sort of that's one of the beauty of algorithms, is that's sort of the implementer's job and not our job, at least in this class. Now, when you leave this class, of course, you'll have to figure all that out, casework and so on, but that's not our job right now. So we now have 2 sorted arrays. We want to return the output of that. How should we do that? Yeah. Yeah, what we'll call it, for now we'll just call it merge. Merge, what merge does is it takes as input two sorted arrays and it outputs the merge of those two arrays as if they were shuffled perfectly together. We'll talk about the complexity and the correctness of merge in a second, but for now just assume it works. Assume that it takes as input, if taken as input two sorted arrays, it outputs one sorted array by merging its two input sorted arrays, right? Maybe it shuffles them nicely. Again, we'll talk about that in a second. Before we do so, let's make some comments on it. I love pseudocode. It's only 4 lines of code. I don't have to do anything more. Second thing, there's a quote about this on proof by induction because it feels like cheating. And it's also true for recursive algorithms because it's almost as if there's looking at this code, it's not obvious how this sorts an array. I mean, it's not obvious what's going on here, you know? It's like you call it on parts of the problem recursively. The magic recursion fairy comes in and fixes that for you, and then somehow the problem is just done, QED. So it's almost like divide and conquer is not a technique that can always apply, but when it can apply, it does so really elegantly, and it's really nice, and it works out really nicely. So that's the second comment we can make about the code. Third is, what would the proof of correctness look like? Again, what technique will we do for this? Exactly. We're going to do proof by induction. Base case, if n equals return A. Okay, that works. L and R, assume by strong induction that these recursive calls on smaller inputs work correctly. We show that this top level recursive call works correctly. So assume these return correctly. So these two arrays are sorted. Now all we would need to do is convince ourselves that merge is correct. So if merge is correct, then merge sort is correct. Done. So the correctness of merge relies on the correctness of, the correctness of merge sort relies on the correctness of merge. That's what we'll have to do in just a second. Questions on that? Let's implement merge real quick. So, you know, binary search gets this speed up because it gets to assume that its input is sorted, right? If the input was not sorted, it would have to first check that it's sorted, and that would take at least linear time. Same thing is going to happen to here. Merge is going to work really nicely because it gets to assume that its input is sorted. So let's define merge as it takes as input two arrays. Let's call them x. We'll call it x1 to k, y, let's say 1 to, I don't know, m. And what we're going to do is, if we have two sorted arrays, what do we know about the merger of them? What is the first element? And let's assume it's sorted in increasing order, right? Like that. What do we know about the first element of the answer? Yes?
Either the first element of x or the first element of y.
Yes, but why?
Because those are already the lowest of their respective arrays. So the lowest of the whole set together has to be one of those.
Exactly. Let's do some base cases. If x is length 0, return y. If y is length 0, return x. If x1 is less than or equal to y1, what we want to do is fix the first element of the output to be x1, and then the rest of it we want to somehow make a decision on. So how should that decision be made? So let's say we know what if we're in this if statement, we know what the first element is of the answer. We're going to return a single array of these two arrays merged together, right? Somehow they're going to be folded in nicely. You have two shuffles, you're going to put them in together. How should we choose the second element, and so on? Yes?
You compare to whichever one was greater of x and y. So in this case, because the x was smaller, x1 was smaller, you compare the next one with y1.
Sorry, to choose the second element, we should do that?
You should compare y1 with the next element of x.
I see. Now, that sounds like it would probably work if I were to think about it more. But the cool part about divide and conquer is that I don't have to. I can just simply hand this job off to somebody else, and they can figure it out. So that's kind of the moral. We're just going to say recursively, and then I don't have to, and we don't, and there's no more work to be done. And the notation is going to be a little ugly. We'll say return x1 dot join, and then we're going to call merge recursively on the remaining elements. Merge of, what is that? x2 to k, y1 to m. Okay, and this dot join notation just means if you have two arrays, they're appended to each other, right? We clear on what's going on here? We choose the first element, and then we're going to append to it in an array sense a recursive call of whatever's left. We just don't have that first element of x anymore, right? Similarly, else return y1 dot join merge of what remains of x, which is all of it, and what remains of y, which is y except the first element. Yes. So this is merge, right? Again, every algorithm we need to argue about correctness and runtime. Before we do, are there any questions on what merge is doing? Okay. First off, the correctness. Why does this work? We kind of mentioned it before, but you pick, these two arrays are sorted, okay? You pick the smallest element of the front of the arrays, right? Suppose it is actually x1. But if x1 is the first element of x, then you know it's smaller than all of x. So you know x1, if you're in this case, x1 is actually smaller than all of x, right? But if x1 is also less than or equal to y1, you know y1 is less than or equal to all of y. So you know that by transitivity, x1 is less than y, and y1 is less than all of y. So you know that x1 is actually less than all of x and all of y. So just with a simple constant time check, you actually know that x1 is the least element of both sorted arrays. If an array is sorted, you always know the least element in constant time. You also know the least element of two sorted arrays in constant time, right? Same thing. And this is just the other case. You pick y1 in the case that's false. So the correctness works that way. The recursion is going to merge the rest of it for us. In practice, what you can think about is if you have two sorted arrays, they're like two stacks of cards, and each time you pull off the min of them, of whatever of the two that you see on the top, if you were to actually execute it, right? By the way, we don't need to do this recursively. It's just more convenient. And it's also, I mean, we're in a divide and conquer lecture. Divide and conquer means you divide the problem up into pieces, you conquer it in the base cases, and then you're going to recombine it into something big. That's what divide and conquer means. Yes?
Can you divide and conquer without recursion?
You can, yes. So like you may know of like the iterative implementation of binary search or merge sort and so on. But, and in fact, those are actually faster if you were actually to do the math, because keeping stuff on the stack and popping stack frames can actually be a little complicated. But keeping track, in terms of runtime, but keeping track of pointers is more complicated for the programmer, but it actually is slightly faster by like 20% last time I checked. But, so most divide and conquer algorithms have iterative versions. But to study the runtime and study the correctness, it's much easier to work as if they were recursive. But that doesn't mean you should think that they're only recursive. It's just a much more elegant thing. Writing recursive code can sometimes be complicated, but it's easy to analyze and it's easy to study. It's not true for if you're beginning with iterative, the iterative version of merge sort and the iterative version of binary search and so on, right? So we see that merge is correct. Questions on that? It does output what it says it's supposed to. It does correctly merge the arrays. Okay, what's the runtime of merge? Yes? No algorithm should ever really be constant. If you think about it. In a pen and paper sense, if you were to do it, if you were to manually do an execution of merge on like pen and paper, it shouldn't take you constant time, right? So, yes?
Would it be n?
Why?
Because when you have the two arrays, like you're putting them into order like
Yeah, you pick an element. How many recursive calls are there, first of all? Yeah, if we assume like k plus m is n, if there's n elements split between these two arrays in some fashion, n elements split somehow, each recursive call we choose one element each time. So there are at most n recursive calls. How much work are we doing at each recursive call? Yeah. So in fact, it's something like t of n is equal to t of n minus 1 plus O of 1. And if you were to expand that out, that's just going to be O of 1 plus O of 1 plus O of 1 plus O of 1, which is just going to give you approximately linear time. Okay, cool. Merge sort takes linear time. Questions on that? Excuse me, not merge sort. Merge takes linear time, sorry. Any questions on the correctness of merge or the runtime of merge? Okay, we don't care about merge, we care about merge sort. So, what is the runtime of merge sort? Yes? Not quite. It's to sort any, here's a counterexample, by the way, for most algorithms, they should take linear time because they have to look at every element. So if you could take less than linear time, that means you ignored some elements, something like this, right? Yes? But how'd you get that? Almost. I mean, so you're not wrong, and we'll prove it today in the general case. It's called the master theorem. But I'm looking for, I guess, the recurrence, right? Yes? How do we know they're log n splits? There are log n splits. I think you guys all have the right intuition, but let's come at it from a slower thing. One more, yeah.
T of n equals 2 times t of n divided by 2 plus O of n.
Yes, and everyone, what you guys said was correct as well, but this is sort of like, we're rewinding a step before then, right? What is the runtime if you're sorting an n element array? First off, you're going to make 2 recursive calls, L and R. Then you're going to run those on inputs of size n over 2. The array is split in half each time. Consider the difference between this and this. Here you decrease by 1 element per each recursive call. Here, the recursive call is working with half as many elements. Then the next recursive call is working with a quarter of many elements, and so on. Then we have to do the recombination and the conquering cost, which is just the time complexity of merge, which is O of n. Right? Now that, that is more difficult to analyze, and for good reasons you guys said that's like n log n. But why is that n log n? We'll have to prove it. So we'll prove that that's basically the point of today's lecture. It's like, how can we calculate that as n log n? If you can't just see this, if you are somehow able to see this and say that's n log n, that's kind of, to me at least, kind of magic. We'll do it formally today. Any questions on the correctness or that recurrence for merge sort? We'll do an execution of the algorithm real quick. Okay, just to show you what goes on in merge sort, let's do one quick demonstration of it. So suppose we have a nice power of 2. Let's say we have 8 elements. Let's say we have this. Five, 2, 4, 7, 1, 3, 2, 6. Right. So what merge sort is going to do, first of all, it's going to recursively call merge sort on itself on the left and the right half. So we're going to go here. That's going to be something, and that's going to be something. So this is going to be an array of size 4. Here's going to be an array of size 4. This is going to be 1, 3, 2, 6. And this is going to be 5, 2, 4, 7. Then we're going to split that again. This is going to be an array of size 2, 5, 2, 4, 7. That's going to be an array of size 1, 3, 2, 6, right? Then we're going to split this again, 5, 2, 4, 7, 1, 3, 2, 6, right? Now, in practice, by the way, when you implement stuff, you don't have to base case all the way out to the smallest thing you can imagine. A lot of times, you base case a little bit before. Like if you're working on a number theory algorithm, maybe you don't base case till numbers are like 1 bit. Maybe you base case till they're like 32 bits or something, and then you do the constant time addition at that level. But here, we're just going to base case out to one array, right? These are what the recursion calls look like all in the division. So we've done the divide. Now we need to like do the conquer. When 5 is going to be a singleton, okay? It's going to be an array of size 1. It's going to hit the base case here that says return A, and then it's going to be returned up. So will 2. So this recursive level is going to have 5 and 2 as L and R. But what happens when it merges them? Yes, they swap. So this is actually going to be, after the return, it's going to be 2 and 5. Same thing here. This is going to be, these are not going to swap. These are not going to swap. And these are not going to swap. Okay? Now, what happens when you merge 2, 5, and then 4, 7? Yeah. What happens when you merge 1, 3, and 2, 6? Yeah. And then what happens when you merge those at the end? One, 2, 2, 3, 4, 5, 6, 7. That sounds right. So observe how, like, in a divide and conquer algorithm, what the parts are. There is a division of problems, right? And when we write the code, we're like, oh, we don't have to worry about it. The computer still has to worry about it for us. So we kind of still do have to worry about it. We first do this division step. Then really the magic kind of happens in the recombination. And the recombination is really when the sorting happens, right? And it's nice that everything, when you look at the recursion tree, it's just this nice binary tree, a verity 2, right? So this is kind of what the execution of merge sort looks like. And again, this takes T of n is equal to 2 T of n over 2 plus O of n. For O of n is the largest merge at each level. But we can really analyze the runtime better by looking at this kind of diagram, looking at this tree. So that's what we're going to do to prove the master theorem in a second. Are there any questions on the execution of merge sort? Do we understand merge sort, right? So why is it called the master theorem? If you want to have a theorem named after you, like a mathematician should be, really you need to do a worse job, because if you do too good of a job naming your theorem after something else, no one will name it after you. The best thing to do is to name it something really vague. And for example, Alan Turing named the Turing machine, he didn't call it the Turing machine, that would be kind of weird. He called it A machines, which is kind of generic and unprecise. So if somebody else comes along and like, let's just call these Turing machines. It's kind of what you bait people into. So the master theorem is incredibly important because it's called the master theorem. But by naming it something really cool, they prevented the theorem being named after the authors, and no one kind of remembers who they are anymore. Right. But what does the master theorem basically tell us? It's in general, given recurrences of a specific form, there's a way we can evaluate it. Suppose we have a recurrence of the form T of n is equal to A times T of n over B plus O of n to the D. It gives us, and this is the recurrence for merge sort. If you notice, it's simply a special case of this, right? A is 2, B is 2, and D is 1 in merge sort. But the master theorem gives us a way to evaluate the runtime to convert something that looks like this to something that just looks like a generic big O that we can quickly analyze. So that's kind of what we're going to do today. But each of these kind of represents something in the code. What do they represent? What is A? If you have a divide and conquer algorithm of such a recurrence, what is A? Yeah. Yeah, basically, it's the number of times that the function recursively calls itself. Here, merge sort appears twice. So here, A was 2. Right? It's the number of, you can think in a literal sense, it's the number of times the function recursively calls itself, right? So A is the number of subproblems. What is B? Or 1 over B? Yes? And what is n to the d? Yes. Yes. It's the conquer value. It's everything else. In Mergesort, it would be considered the time for the base case, the time to call merge, the time to copy arrays over. Now, we don't actually do any array copying. We keep everything in memory and we just sort in place. But it would be all this, anything else would go into that n to the d for that level, right? So we want to evaluate, and basically you can improve a runtime of a divide and conquer algorithm really by only improving these three things. If you can improve these three things, then you can improve the runtime of an algorithm. In fact, you can make trade-offs. You can, for example, you could reduce A perhaps by increasing D. So we will see some algorithms with that. And by doing so, that actually will speed up the algorithm runtime, right? Let me give you the example computation, right? So we'll do here. So suppose we have a recurrence of the form t of n is equal to a t of n over b plus o of n to the d, right? Let's look at the same execution tree for this problem. We start at some root and we have a couple branches, right? And our branching factor is going to be a, right? So we have a branches. And each problem there is of size n. But when we have a subproblem, how many recursive calls are there one level below? I'll draw the picture. Each of these is going to be, each of the A recursive calls is going to have A recursive calls. So how many recursive calls are there at the second level? Yes. Yes. And then what about the third level? Now those are the number of recursive calls. Each recursive call does a certain amount of recombination. The top level does what? How much work does the top level do? It doesn't have any recursive calls, let's say. It's just recombining things. Let's not measure the number of recursive calls. It does the recombination cost, which is O of n to the d, right? The next level has A recursive calls, and each one of them does how much work? It's almost n to the d. When you work on the recursive call, it's not working on an input of size n, it's working on the size of the subproblem, which is n over b. And it does that with time, n over b is the size of the problem at that level, to the d, which is the time recombination cost. And it does that 8 times. Then the third level is going to have a squared times the work done at that level, which is going to be what? How big is the subproblem at the third level?
N over b squared.
And so on. I think I'm off by 1. No, I'm not. Good. Right. Now, when does this stop? We keep doing this work at the intermediary levels when we hit the leaves. How long does a leaf take of such a computation? It takes constant size. If it's not constant, we haven't divided enough. The base cases should take constant time. If you are not constanting out, let's not even think about that. The base cases should take constant time. So we're going to sum the work done at each level, and then we're going to add the number of leaves times O of 1, because that's the time it takes for each leaf. Right? So now we just need to know the number of leaves. How many leaves are there in a tree? This is in such a tree. This is a difficult question. Well, we need to know the depth of the tree, right? In a binary tree, what's the depth? If you have depth k, how many leaves do you have? Yes, 2 to the k, okay? So we want to figure out the depth of the binary tree, and if we have a array tree of depth k, we have how many leaves? Yeah. So we need to figure out the depth, right? How can we figure out the depth? The depth of the tree is when we can stop dividing by the subproblems, right? So whenever this thing is a constant, we're done. So the question is, for what k is n divided by b to the k equal to O of 1? Right? That's the depth that we stop dividing at. I can rewrite this to say that n is equal to b to the k for what k? And therefore that implies that k is equal to what? Log base b of a, right? Is that right? A of b? No, that's right. Okay. So then the number of leaves is what? Someone say it? B of yes. Oh, my bad. Thank you. Okay. Now, if you guys know your log rules, we can rewrite this.
Log n over log b.
That's a different log rule. Yes, that's also correct. You can derive that from what you said. It would take like one extra step. But you can, basically, if you have something to the log of something, you can swap those. Right? So we swap the a and the n here, and we get this. Right? N to a constant. And the reason we like this is now a constant. So it's like a polynomial. It's like n to the something. Right? Okay, so we have parts of the runtime. We just need to like sum everything up and make it all nice. So the runtime in general, if you have a recurrence of the form T of n is equal to a T of n over b plus O of n to the d, then T of n is going to be equal to the sum of such levels from, let's say, I equals 0 of a of I times O of n divided by b to the I to the d. But to what does this sum go to? What is the largest term of this sum? Sorry, say it. K, which is log of what is it? Bn. Log base b of n. Okay? That's the work done at each level. We also need to sum the amount of base cases we hit, which is going to be O of n to the log base b of a. Okay, that's the answer. QED. Now, of course, algorithms. We're not going to leave it like that. You take big O, you guys know that you take the dominating term. If you have an n plus n log n algorithm, then you know that it's n log n. So we need to somehow make this may have a dominating term. There's a lot of noise there. Let's simplify it. And this is the statement of the master theorem. T of n is going to be into 3 cases. Okay. When you have a divide and conquer algorithm, just like if you think about a tree in nature, either the leaves are the heaviest part and the branches are really thin, or the branches are really thick and it has almost no leaves, or there's some kind of balance in between there. So let's suppose that, what is the first term of this sum? Correct. So that first term, if the sequence is decreasing, that first term will be bigger than that thing. So then this thing we can ignore. So if D is greater than log base B of A, then T of n is just what?
O of n to the d.
Ignore everything else. If D is bigger than log base B of A, we're fine. Now, what if D is less than log base B of A? This corresponds to the leaves, there's a lot more leaves. They're not heavier, there's just more of them. Then the branches get thicker. How many, what's the runtime if D is strictly less than log base B of A? Yeah. Okay. We're missing a third case. What if D equals log base B of A? This corresponds to like a perfectly balanced tree, where each level, if you were to take a saw to a tree, you know, like, right? Each level weighs exactly the same. The branchingness is exactly as much as the work done at each level, right? What would we take in our sum here? If there is no, we can't just take a biggest term, okay? So what should we do? This is, I think, a tough one. If you can't take, if none of these terms are maximal, then we know they're actually all equal. So everything in the sum is actually equal to what? Yeah. Power of what? What's the first term? They're all equal, so what's the first term in here? Almost. Yeah, the first term in here is O of n to the d. The second term is equal to it. It's O of n to the d. The third term is equal to it. It's O of n to the d. They're all equal. And in fact, if d equals log base b of a, then that's n to the log base b of a, which is n to the d. So you have n to the d added a bunch of times to itself. How many times is it added to itself? Yeah. So the answer is going to be what? Almost. N to the d log n. If d equals log base b of a, you throw a log on there. That's all you got to remember. You compute b to log base b of a, and you compare it with d. You take the bigger one. If they're equal, you throw a log on. That's how you remember the master theorem. This is the master theorem. These three cases, take a runtime like this. Don't even look at it. Just take the a, the b, and the d, and then you get these three things. That's how you compute which one is faster, right? Questions on the proof of the master theorem? Sorry. Yeah. Do we believe it? Any qualms? Any like, well, we missed this, or any disagreements? All right, let's apply it. That's the easy part. Okay? Notice it doesn't work for certain things where it doesn't divide out nicely. For example, merge. We still have to kind of like manually analyze it. But those cases are much easier, right? So the merge sort recurrence was T of n is equal to 2Tn over 2 plus O of n. A is equal to what? B is equal to what? And D is equal to what? Okay. What is log base 2 of 2? Okay, which case are we in? The second case, because D equals log base B of A. Right? Log base 2 of 2 is equal to A, which is, excuse me, is equal to D, which is just 1. So in fact, our runtime of this is what? There you go. That's kind of why when you jump to saying, oh, we divide out by 2 and it's half as many, it's just log and log n. There's a little more complicated work to be done behind the scenes, right? That's the proof of why it takes, merge sort takes n log n. But that's not all we can prove with the master theorem. We can prove everything else with the master theorem. Suppose I didn't ask for a merge sort where we divided it in 2. Suppose and we suppose I ask for dividing in 3. What is T of n if we divide it into 3 arrays, a left, a right, and a middle, and each one is a size 3? It still takes O of n for us to do this recombination stuff, this merging. A is equal to 3, B is equal to 3, and then D is equal to 1, right? What's the runtime of this merge sort? Yeah, it's the same. Why? Log base 2 of 2 is equal to log base 3 of 3 was equal to 1. So if you have a divide and conquer algorithm, if the number of subproblems is equal to the size of the subproblems split, it doesn't really matter. Now, it does matter if you can change the number of subproblems by changing the size of the subproblems. But if you keep these things, 2 halves is the same as 3/3 and 4/4 and so on. That doesn't actually change anything about divide and conquer algorithms. There's no smart way around that. You can change the number of subproblems by keeping other things the same. That would improve things. If you can change the size of the subproblem, keeping other things the same, that would change that. But here, that doesn't have any effect. So a 3-array version of merge sort doesn't do anything at all, in fact. Right? In fact, it might just make it more complicated. Okay, let's try some other stuff out. Binary search. Suppose we have recursive binary search. Right? What's the recursion for binary search? T of n is equal to what? First off, how does binary search work? We have an array, it looks like this. Right? Let's say it's sorted. We're trying to find the index of an element. What do? We look at the midpoint. It's lower or higher. We play hotter or colder, right? If it's on the left side, we just say we say no to that, and then we recurse here, right? And then we try again. Is it here? We say no, and then we recurse here, and so on, right? Binary search does not have to be recursive. But if we think about it recursively, we can analyze the runtime better. I think the better implementation of binary search is actually iterative. You have 2 pointers, and then you move this here, and then you move this here, and you do something like that. But that's nice because it leaves the memory in place. Let's suppose we don't care about that, and we're just doing a recursive version of binary search. What is A, B, and D? T of n is what for binary search? A is 1? Why? Yes, we only have one recursive call. Even though we're splitting it in half, we're not recursing on both sides. That's the difference between merge sort looking like this and binary search looking like this, right? That's a big difference. So A is 1 here, and what is the size of the subproblem? What's the work done at each level? It's a constant, but why? I mean, it's a constant, yes, but why? It's a single comparison, so we say it's O of 1. Now, A is equal to 1, B is equal to 2. What is D equal to? Yes. Why? N to the 0 is equal to 1, right? Let's plug these into the master theorem. What is log base B of A, which is log base 2 of 1? Okay, which is equal to D. So we're in which case? We're balanced. So what is the runtime? O of n to the 0 log n, which is going to just be log n. Done. Easy. Questions on that? Okay. Next, we'll use the master theorem very extensively in the next 3-4 days. So that's all I have for you guys. See you on Wednesday. I'll be around after class if you have any questions.